everybody. So we all know as developers that sometimes we have some bugs in our brain. So we have an example here I heard a do yesterday. So for this, we need some tools like this to try to find the bugs our brain is introducing in our applications. So for making memory profiling on HPC applications. So those tools, I make them because I made my PhD on developing a memory allocator for high performance computing, so for supercomputers. And I learned a lot of mistakes applications are making on those things today. So I developed MALT at the Exascale Computing Research Lab after as a postdoc, which is a memory profiler for malloc. And NUMAPROF as a side project as CERN later to profile the NUMA aspect of the memory management. So the motivation is that today, mostly in HPC, we have really huge space of memory to manage. We can find today some servers with roughly terabytes of memory. It's really huge to handle in the operating system. There is some issues for performance. We have a lot more distinct allocations to allocate all those objects in this big space. So, the example, during my PhD, I was working on an application making 75 million allocations in 5 minutes. So when you develop a malloc underroot this thing, this is a little bit challenging. And on top of this, we are using multi-threading. So I was working on a big cluster with 256 threads on the same motherboard. And all of this is done inside really huge application, mostly C, C++, or Fortran for HPC, which can be, for the application I was working on, 1 million lines of code. So of course, if you want to understand what happened on this thing, you need some tools, because looking the code by your eyes, this is doomed. And you adapt to this, now we have the NUMA layout, so the non-uniform memory accesses, which also adapt to the complexity. And in the end, we are against the memory wall today, which was discussed a couple of years ago, but now we are really in. So the performance can really reduce a lot the performance of your application due to memory. So my work today, from my PhD, you need to well understand the memory behavior of your, I said HPC, but it's also true elsewhere, application. So just to give you an example, this is a big application I was working on. So 1 million lines of C++ code, running on 128 cores, or 228 cores, 16 CPUs on the same motherboard. So a big NUMA node. This was really challenging on Linux Underwood. And just by changing the memory allocator, you can see the default one from Linux, glibc, gmalloc, and tcmalloc, which were mostly the top allocators we have today. Just by changing the memory allocator, you can change the performance of your application by roughly 35%. I mean, this is not 2% or 3% we can expect. And even more, I mean, when I made my PhD, I was implementing my memory allocator, taking account of all the issues I was seeing on those things. And just by improving the communication with the Underwood operating system, I was able to gain 20% of performance on this application. And again, taking into account the NUMA, 58% of improvement, just by changing the malloc. So, I mean, this is an extreme case. I mean, there is not so much application with such large gaps, but still, when you start to look, there is a lot of application where you can gain 10, 20%. This is quite common in HPC now for this thing. About memory consumption, same thing. On the same application, so this is on a smaller machine, and the worst case I have seen with this one. On 12 cores, you just change the memory allocator and you look on the memory consumption of your app. And then you can see that changing the memory allocator can change from a factor 2 the memory consumption of your application, which is, again, not 10%. So if you really want to understand a little bit what your application is doing, in this case, you need tools. You cannot just look by eyes and try to pray that you will understand at some point. So for this, I first developed MALT, which is a malloc tracker to try to understand the memory management issue. So how many times I'm calling malloc, do I am making small allocation, big allocation, short life allocation, all those stuff, which can at the end impact the performance of your application. So I try to track all the mallocs in the code and report the properties of those allocations to understand the behavior of the thing. So in the principle, this is the same ideas on Valgrind and Kcachegrind, which are nice for performance profiling, but providing source annotation, call graphs. And at some point, I was starting using Kcachegrind as the graphical interface, and was stuck because I wanted to have also some other metrics I was not able to put directly in Kcachegrind. So at some point, I made my own graphical interface on top of it, which is web-based. So you get this kind of thing with source annotation, so you can see directly here the values annotating the lines. And when you click here, you can get the details on which call stack lead to this point, the details value you want to get the properties of this allocation. So you can quickly understand what happened. And I will not put all the examples. You also have some time charts to understand the dynamic behavior of the allocations inside your application. So here is for example, the sizes you allocate over time, the lifetime of the segments you are allocating depending on their size, all the stuff which can impact the performance of your application. So then I'll move to NUMAPROF, which is a really similar tool, taking most of the code from MALT at some point when I developed it. So the idea is about NUMA. So NUMA, when you have two CPUs, we know that today we have a memory attached to each CPU. So if you access to the local memory, this is quite fast. But if you access to the other one, you need to go through the second CPU, and it starts to cost a lot. So again, you need to take care of the placement of your memory, which is a big challenge today in HPC. And for this, I developed NUMAPROF to try to detect the remote accesses and again report you on your source code to say this line is making these accesses, this malloc has at the end generated these accesses, and to try to understand the behavior of the thing. And also to detect the unsafe. I mean, sometimes you can say the Linux kernel will detect automatically where to place the memory. This is what mostly we done every time. But this can be wrong, and I also try to detect this thing to push on to the developer to maybe you need to control this thing. So just to get some views, one example, you have a summary view, so telling how many remote local accesses you are making, uncontrolled accesses you are making. And for example, this small matrix here, which show NUMA node 1 is accessing to memory to NUMA node 1, and ideally you should get a diagonal if you want a nice application. And most of the time it's not what you get these vertical lines which can impact the performance of your application. And here you get the memory distribution over the NUMA nodes, for example, just to check if you allocate more on one node or not. So you have a lot of charts like this in the tool, so I just show one. And again, the source annotation with some details. If you put your mouse on the annotation, you get all the details of the accesses you are making on this line. So you can really dig in the thing and try to understand what happened. So just to get some success I get with those tools, so MALT, when I was developing it, I'm using it for my own development most of the time. So at CERN, I was managing a code of 32,000 lines of code in C++, and I was able, by saving some malloc call, to reduce the CPU usage of this application by 20%, which is, I mean, not null. And it was done in roughly, let's say, 15 minutes. So nice. We improved also 2 commercial simulations while I was developing the tool at the Exascale laboratory. And the profiler is now also able to profile the LHCb application, which is 1.5 million lines of code. I mean, I don't have results yet, but I mean, the tool is working on this thing. So, I mean, because it does require some patches to be able to support such a big thing. NUMAPROF, when I was developing it, I took one application from CA, so a numerical simulation. And in 20 minutes, without knowing anything of the 8,000 lines of code, an MPI application, I was able to gain 20% of performance in 20 minutes without knowing anything on the code. So, I mean, it was quite nice. I also detected a Linux kernel bug about NUMA policy. So it was detected by Red Hat 2 weeks before, so I didn't have to report, but at least the tool was showing me directly the thing, so it was really nice. And it was also validated by a CERN PhD student, which was checking the NUMA correctness of his application. So in this case, it was nice, so no gain, but at least the tool has confirmed that he made the thing right. So that was nice. So both of the tools are now hosted on GitHub since roughly 1 year. On memtt.github.io. You will find a nice website if you want more screenshots to see what you can get also. And if you are interested in memory management for high performance computing, you can find all the documents I wrote during my PhD on this website, so you can get many pointers to everywhere from this. So thanks. For what? No, not yet, no. Yeah, the question was, do I have support for NVD memory, non-volatile memory, and this kind of stuff? So currently not, but at some point they will be exported as NUMA nodes. So I mean, at some point I will, I think, get something, yes. And I have an explicit support for NC DRAM of the kernel for this, the knife downing from Intel. Yep.
Any more questions? All right, well,
Nice. Thanks very much.